All right, today we are continuing with graphing rational functions. Now, whenever you have to graph a rational function, you have to look for things called poles, vertical asymptotes, and horizontal asymptotes. Right now, we're going to discover if we have any holes, if we have any vertical asymptotes or horizontal asymptotes in this problem. We're going to go over those rules here in just a bit. But before we do that, something that you, as an individual who are watching this video, need to understand how to do is how to factor simple trinomials like this. You need to know how to factor these guys. And if you don't know how to factor these guys, well then hopefully I can give you a little bit of information to help you know where to start. And I'm going to write where you start. I'm going to start every single time with the factors of the constant. Now, if you're not sure what the word constant means, there's a constant in this problem that does not change. And this number 3 is the number that's considered to be the constant. Because in this problem, that 3 will always just be a 3. This negative 4 right here will not always be a negative 4, because if I plug in a 1, it'll be a negative 4. But if I plug in a 2, that'll become a negative 8. If I plug in a 3, it'll become a negative 12. If I plug in a 0 right there, that zeroes everything out. But this number 3 will always be just the number 3. So let's start with the factors of the constant. The cool thing about the factors of 3 is you only have a 3 and a 1. That's it. So I know I'm going to have an x here, I'm going to have an x here, I'm going to have a 1 here, I'm going to have a 3 here. We got to figure out how in the world can I get a 1 and a 3 where they add together to equal a negative 4, but when you multiply them together, you get a positive 3. A 1 times a 3 is a positive 3, but a 1 plus a 3 is not a negative 4. So what do I have to do? Make them both negative, right? Make them both negative. So we have x minus 1 and x minus 3. Those are the factors of this simple trinomial. And this is a method that you could always use to see if you can factor it if the coefficient in front of the x squared is simply a 1. So right now, we've got a problem. The problem is we've got a big old number up here. We've got this polynomial that doesn't start with an x squared. It starts with an x cubed. I wonder if we could test to see if x minus 1 is divisible into this, or if x minus 3 is divisible into this. Well, we do. There's a process called synthetic division that we have done earlier in the year. We're going to practice synthetic division right now. Here we go. Let's do some synthetic division. In order to do synthetic division, we're going to list how many x cubed, x squared, x to the first, x to the 0. In order, how many of them that we have. Then, over here, I'm going to put a number right in here that's going to be a root. We're going to check to see if this is a root that goes into this problem. Now, we have two factors. What are our factors that we're going to test? We can test an x minus 3, or we can test an x minus 1. Then put a nice long line. Okay. Now, let's scroll up and think about how many x cubes we have. We have 1. So you're going to start with the number 1. Then you go over here, you got negative 2x squared, so I'm going to write a negative 2. X to the first, we have a negative 5. And our constant at the end, I believe, is the number 6. So right now, we need to test either x minus 3 or x minus 1 and see if it's divisible into this polynomial. What do you guys want to do? You guys choose. X minus 3, x minus 1. Which one? 1? Okay. So if we check this factor right here, if it's x minus 1, what number am I going to put in right here? I'm actually just going to put the number, right, positive 1. Because 1 minus 1 is 0. We want to see if this is a root of this particular polynomial. Now, once you've figured out which number to plug in right here, drop this number down. That's a 1. What am I going to do with this 1 and this 1? We're going to do what with them? Multiply. 1 times 1 is 1. Now, if you forgot this process, then my suggestion is put the word add between the negative 2 and the 1 to remind you need to add these together. Negative 1. Multiply these together. Negative 1. Add the negative 5 and the negative 1 together. Multiply the 1 times the negative 6. Add these together. And you get a remainder. You get a remainder of 0. And that's actually a good thing. If you get a remainder of 0, that means we know what? We know x minus 1 goes into that. Okay? So, what does this represent? This represents how many x squareds we have. This represents how many x firsts. And this right here represents the constant that we have at the end. So this is x squared minus x minus 6. Alright, so since this is what we have left, I wonder if there are two numbers in the world when multiplied together equal to negative 6, two numbers that add together to equal negative 1. And what do we always start with? We start with the factors of the constant at the end. What are the factors of 6? The factors of 6 are a 6 times a 1 and a 3 times 2. Is there any way we could use a 6 and a 1 or a 3 and a 2 to somehow get us to a negative 1 when adding them together?
No.
Minus 3 plus 2 minus 3 plus 2. So this actually factors 2. X minus 3 and x plus 2. Holy cow. That big old x cubed polynomial had how many factors? Not one factor, not two factors. It actually has 3 factors. So let's list all the factors in order, okay? Here we go. F of x equals x minus 1 times x minus 3 times x plus 2. Now, if you're watching this video, you're like, I wonder what that multiplies to. I'll tell you what all of this multiplies to. Right? All of this multiplies to this right here. It all multiplies to x cubed minus 2x squared minus 5x plus 6. I'm not going to multiply all that out because that would take a long time. I'm just going to keep going. All right, now that's all over. What did we factor the denominator to? X minus 3 and x minus 1. I'm just going to, for no reason at all, I'm just going to write x minus 1 and x minus 3 here. Just because it's the same thing, but not for any particular reason. Now, everybody, just for this particular lesson, what is that whole top number actually equal? I'm going to look over here at Leon's paper so I can look at it carefully. Oh, that one, if I multiply it together, equals x cubed minus 2x squared minus 5x plus 6. That's what that one equals. And what is the denominator equal? That equals x squared minus 4x plus 3. But this one factors to all of these, and this one factors to both of those. Now that we have everything factored, now we can figure out if we have vertical asymptotes, if we have holes, and so on and so forth. So, everybody, let's get our red pen out, and what do we need to do? Mark things out. What can we mark out? X minus 1. X minus 3. Now, whenever you do this process, what have we just found? We have found holes. Not the movie. Just a point of discontinuity. We have a hole where x is equal to a 1. Because if you plug in a 1 right there, 1 minus 1 equals 0, and that's bad for a denominator. We have another hole at x equals 3, because 3 minus 3 is 0, and once again, that's bad for the denominator. Now, what is the only thing we have left standing in the numerator? That's it. So all we have left is f of x equals x plus 2, where there actually are two holes. There are no vertical asymptotes. There are no horizontal asymptotes in this problem. Okay? So basically, that would be your graph. So right now, we're going to go to the graphing calculator really quickly. We're going to type this in. Y equals, okay? We're going to hit alpha, y equals, enter. And we're going to type in x to the power of 3 minus 2x squared minus 5x plus 6. And in the denominator, we're going to type in x squared minus 4x plus 3. And when we hit graph, it's kind of funny. Here's what you see. See a straight line, because that line is actually the line x plus 2. Now here's what your graph does not graph in this particular case. It does not graph a hole right here where x is equal to a 1. It doesn't graph that hole. And right here where x is equal to a 3, it doesn't graph another hole right there. Okay? So we actually have two holes. So if I were to ask you to graph this rational function, you would graph the line, but what would you put on your graph? You would put a hole where x is equal to a 1 and where x is equal to a 3. Now check your table. Does everybody see in their table? We have an error at 1 and we have an error at 3.